Hi there, everybody. Welcome back again. I want to apologize, first of all, for waves number 4. That was way too long. So today, waves number 5, I promise you, it will go very quickly. We're going to bust through this. It's pretty easy, and we'll be done very, very quickly. All right. Today, you're going to need both the equation sheets and the sheet of constants. We're going to use those just a little bit. So it'd be good to look onto those. And I don't even think you're going to need many colors today. On your equation sheet, go over to where it says waves and optics. That's on the back, and it's going to be up on the upper right-hand side. And we're only going to use our first equation here, which is the velocity of the waves equals frequency times wavelength. Now, here's the thing to remember. For the most part, sound waves, and light waves, anything, the flavor of the wave is the same. Let me say that again. For the same flavor of wave, the velocity is the same. So light waves always go the same speed. Sound waves always go the same speed. Now that's not always true, and we'll talk about that later. But for the most part, that's going to work for you, and I'll show you how that'll help here in a minute. Let's talk about sound first. So, like I said, all sound waves go at the same speed. Low notes and high notes all are traveling from my throat to your ears at the same speed. Okay? Turns out that speed is about 343 meters per second. So, no matter what note I'm singing, it's traveling pretty darn quick between you and me and you. All right? If I want to change that a little bit, here's what I do. I change the temperature of the air. So think of it this way. If I change the temperature of the air, it's kind of like stretching a slinky or making the slinky looser. And we did that in a lab, and I hope you remember that really affected the speed that the wave went up and down the slinky. Same thing with air. Heating up air and cooling it off, hot days, cold days, air actually goes at a different speed. Or sound goes at a different speed, I'm sorry. So now let's plug that in. Velocity equals 343, and that equals the frequency times the wavelength. Okay, let's move that up to the top of our page here. And let's think about that for a minute. Let's say the frequency we make higher and higher, a bigger number. So I go from here and I start talking higher and higher. As I do that, if the frequency is increasing, so if that number's going up, what do I have to do to the wavelength over here to make that number stay exactly the same? Well, if the frequency value is going higher and higher, bigger number, that means the wavelength has to be decreasing. So the wavelength, the distance from crest to crest has to be getting smaller. So let's draw a wave. Let's draw a big long one. All right, and let's draw a short one, like this. Now, if these are traveling at the same speed from left to right, 343 meters per second. All right. Let's think about this. This one has a big wavelength. This one has a little wavelength. Think about what has to happen to the frequency. A large wavelength means small frequency. Ah! Don't write that down. Small frequency. And a small wavelength has to mean a big. Boy, I am just asleep at the wheel today. A big frequency. Can you see that? Has to happen that way. I really hope you take a second and try to get a feel for that. Imagine these waves going by you and a low note. That's the one up on top. A low, low note means the waves, while they're speeding along the same, it takes longer for them to go up and down as they go by you. Now, if we have a really high note, we're down here, and the wiggles are going by much more quickly. The waves are going the same speed, but the wiggles are going by differently. Okay? How'd we do? Switching down to light. All right. Light has a different speed. Light is screaming fast. 3 times 10 to the 8th meters per second. That is just wicked fast. That number happens to be on your sheet of constants in the box on the upper right-hand side. You should find it so you know how to use it. Now, they will not give you in the test the speed of light because it's on your constants sheet. If you need the speed of sound, however, on the test, they will give that to you, and they'll tell you which number to use. Okay? So, let's do a similar thing. Let's think about light. Now, at first, all we're going to talk about is light that we can see, visible light. And here's a little table I made of the light that we know, Roy G. Biv. Okay, red, orange, yellow, green, blue, and violet. You probably learned blue, indigo, violet. Well, turns out they kicked indigo out. There's a neat little story about that, which I'll tell you in class, if you guys remind me. But yeah, indigo is not in the rainbow anymore. All right? So you don't know this, so I am just going to tell you. All right? Red has a small frequency. Okay? I'm going to write this in black here. Small frequency, and it increases to a big frequency. So I want you to fill in the wavelength part, and I hope you get big frequency down to small. Boy, I didn't write that very nicely. Hope you can read that. Okay? Here's what I'd like you to do. Draw a wave. Okay? Let's draw the waves over here. What do they look like? The red one I'll draw in red. It has a large wavelength. So relatively speaking, it's like that. Okay? And if we go down all the way to the blue and the violet, it's going to go by you, and it's going to have a much smaller wavelength. So it's going to look like that. All right? That's pretty much all I wanted to say. And here's our quiz. I want you to tell me what the frequency of a sound wave is that is exactly 1 meter long. Okay? So once you do this, I'm going to play this note in class for you, and we're going to imagine this 1 meter long note going by us. All right? Have an awesome day. See you tomorrow.